Okay, welcome back. This is the high introduction to YouTube part that could have come before class. YouTube, you don't know, this is a skipped video. So like and subscribe. But what we just saw, you'll be about to see. Ae Kyong Jung will be teaching DCMs in just a moment on the next video of this sequence. But for this video, I wanted to talk a couple things. So today's class is about higher order and method factor models. Given the time we have, it's going to be somewhat of a quick lecture. I'm going to keep it at a higher order level of topic to go through it. The other thing I want to note is I assigned the last homework, which is to basically to take your data that you have volunteered during homework one that you have, and to analyze that using some type of measurement model, an IRT model. So this is taking what's novel. So in homework, the previous homework 3, you had gotten experience with CFA, doing some confirmatory factor analysis. Now I'm asking you to switch that to IRT. You submit the homework on December 1st, which is a Monday. I will turn around to you on December 2nd. By the end of December 2nd, so with my feedback and comments, and then you can make a presentation about what you did and what you found, addressing and fix whatever the comments say, and that'll be the last class that we have, right? On the Wednesday of the last class, December 10th, I think it is. That last class will be a Zoom class, in part because it's easier to get you to share screens and not have to worry about your slides and materials and so forth as well. You're welcome to sit in this room if you want, but the other part of that is I have some travel that day. I'm supposed to go to a meeting on the following day. So I don't know where I'm going to be where I take that class, but I won't be here in Iowa City. Somewhere on Earth, preferably. Hopefully still around and kicking. So I know it sounds really morbid. Isn't that like a few weeks from it? Yes. Yes, I'm going to make it through the end of the semester. That's my goal. Any thoughts, questions, or comments about any of that? No problem. No, just answer the questions, but do the analysis. Yeah. And Tevin, you said there was a surprise or? Oh, no, no. I thought you were like, I looked at the homework and I am surprised. I thought you were saying, okay, that's good. That's good. Yeah, just answer the questions. Basically, what I want you to do is to answer the questions. It's supposed to get you to think about doing. You have to do the analysis. You have to sort of think about what it means, and then what I think I've found students have told me in the past has been valuable is seeing each of just the concepts that you're putting into the model itself. So when you give the presentation, and again, I'll make a sheet that says what to include in your presentation. It'll be 10-minute presentation tops. But basically, a lot of that presentation is what's the construct you're measuring? Can you share some of the information about the items? And then what did you find from the model? And I'll give you some details about how to answer. So basically, it's that. The feedback I've heard from students are just hearing about the different constructs that people are measuring and how they're measuring them is very helpful to sort of generalize what they're learning. So that's the purpose of it. And then that allows me to give you a database project-like thing that's small enough in scope to fit the class, but not also wreck your life in the process of doing that. Okay? Okay. So with that, I'm going to stop.
Hello, everyone. I'm Ae Kyong Jung, and I'm a PhD student at Educational Measurement and Statistics. Thank you for having me, and I really appreciate to give me the chance to have a lecture today. Today, I'm going to talk about diagnostic classification model, and I start with comparing with the familiar models, CFA, confirmatory factor analysis model, and item response theory, or IFA, with the DCM model. And then I'll start with single dimension and with the terminology which is used in the DCM model. And then I'll extend it to multiple dimensions. And then the DCM is composed of two different parts, measurement model part and the structural model part. So we'll dig into that. What was the CFA model? When the response data are continuous, and when we are assuming that latent variables are continuous, we use the CFA model. And what about the IRT model? When the responses are discrete and the latent variables are continuous, that was a big difference with the CFA model. And what about the DCM? The big difference is its latent variable is discrete and the responses are discrete. So when we want to classify a student based on the latent variables, and when we want to decide that they have mastered some ability or not, some specific latent traits or not, then we want to use the DCM model, DCM. These 4 people take a math ability test, and what kind of information can we get after we take this test? We're assuming they get the continuous latent variable. So the blue students has more math ability than pink person. That's what we can get from this continuous latent variable. And also we can get red scored in 70th percentile, which means 70% of the people are below red person. And also we can tell the green person score 240 on the test. So we can compare each student's relatively from the continuous latent variable. Then do you think the CFA and the IFA or IRT model can answer these kind of questions, like why the pink is so low, or how much ability is enough to pass, or what math skills have the student mastered? To answer those kind of absolute things, we need a specific cut scores. To diagnose that based on the cut score, we can give some kind of information like a pink score below the cut score. So this pink person need a remedial course for the math. We need that cut scores to diagnose student into 2 different classes and to say, oh, they have mastered the math or not. To set the cut score, then we need extra processes like standard setting. Standard setting is a process that gathering the experts who are expert in the math, and they discuss about the cut score. So it takes a lot of money and time to set the cut score. But in the DCM, we can diagnose people into 2 different parts based on the latent traits. So we don't need that kind of processes. So the purpose of the diagnosis, as you can see from the name of the diagnostic classification model, we can diagnose people based on their latent traits. So we're going to focus on educational measurement field where we need a diagnosis. So there are some competencies or skills, latent traits, or latent characteristics that a person has or has not mastered. And for example, in the math test, we want to specify latent traits specifically, not just a math ability. So for example, we can say like convert a whole number to a fraction, or separate a whole number from a fraction, and simplify before subtracting. We can specify these kind of multiple latent traits in the DCM. And also, not only in the educational measurement part, we can do assessments for the psychiatric. For example, the Diagnostic and Statistical Manual of Mental Disorder Criteria. This is a criteria for diagnosing people have a mental disorder or not. So that is also a field where the diagnosis is necessary. And also we can do personal selection based on the diagnosis. So when company hire people, they want to see if the people have certain traits they need or not. So we can diagnose people in that case, like personnel selection case. Let's see the single dimension of the DCM. This PEP diagram is already familiar to you because we saw this a lot in the CFA model. And the different thing is this latent traits is divided into 2 different parts. This latent trait is also called attribute, and this attribute is typically synonymous with the term latent traits and latent characteristic that we cannot see. And also this attribute has a history of use in a literature and factor analysis. And this Q matrix is showing this path diagram in the matrix sense. So we can see this item 1 is measuring math or not. Item 2 is measuring the math or not. Now this is a single attribute, so they're all 1 now. But if we have more attributes here, then some might be 0 and some might have 1. So we can indicate this matrix with 0 or 1. So we can tell if item is measuring this latent variable or not. This arrow should be in here. So this Q matrix doesn't seem very necessary in here, but if we have multiple latent variable, then it will be very important. This is the respondent profiles. Respondent profile is also called classes or attribute pattern and denoted with attribute alpha C. C means a class. So as we have a single latent trait, it can be 0 or 1 because I said the latent traits are discrete in DCM. So one profile or one class where they have not mastered the math, then it will be 0. And the profile or class 2, which has mastered the math, will be 1 here. So 0 or 1 is the only value that we can get from the DCM. But in the respondent profile estimates are in the form of the probability of master, probability of the class. So when we estimate after the DCM, we can get the probability of attribute class 1 and the probability probability that if students are classified into 2 or not. So these are, at the end, the estimate is the probability of each classes. Let's compare the CFA and IRT and DCM model in the equation sense. The CFA model, we said the continuous responses are continuous and the latent variables are also continuous, and it's denoted with the theta here. And the two-parameter logistic model, we're assuming the response data are discrete. So we need a logit function or probit function, but in two-parameter logistic function IRT model, we use a logit. So this one is represented like this. And the theta is continuous, like CFA model. And the LCDM model, which is a log linear cognitive diagnostic model, which is a one type of DCM model, we use logit function because the responses are discrete. And also we represent the latent variable as alpha because it's discrete. So it looks different with the theta here. Let's see the multiple dimension type. The set of skills or set of competencies or set of latent traits, those are all same words, terminology, represent the multiple dimensions of elementary mathematics ability. In the math test, we want to diagnose, oh, you have mastered addition and subtraction, but you have not mastered the multiplication and division. So you need to study more about this part. We don't want to just say, you have mastered math. You have not mastered the math. We want to give a detailed information, detailed feedback to them. So other psychometric approaches also have been developed for the multiple dimensions. So classical test theory have subscores, and CFA also can assume that 2 factors or 3 factors, we can assume in multiple dimensions. And also multidimensional IRT theory, IRT is also assuming multiple dimensions. But the problem is the reliability of estimate is often very poor for most practical test length. So to increase the reliability, we need a longer test. That is one issue. And dimensions are often very highly correlated. So if you see this is a handout from a previous CFA class. And if vector correlations are over 0.85, then we suggest a simple structure. It means one latent variable instead of multiple latent variables. And also, if we are doing the item calibration in the multidimensional IRT sense, then we need a large sample sizes. So that is we need a lot of cost to gather many samples, so we might don't want that. DCM provide respondents valuable information with fewer data demands. The valuable, if you see this graph, this is showing the reliability between IRT with 1 dimension, IRT with 3 dimension, DCM with 1 dimension, DCM with 3 dimension. And this x-axis is item per dimension. So if you see the blue line, which is IRT 1 dimension, if we want to reach the reliability 0.8, then we need very high number of the items per dimension. So it was 34 items. But if you see this purple line, which is a DCM with 3 dimension, to reach the reliability 0.8, we only need 6 items per dimension. So we have 3 dimensions, so 6 times 3, we need 18 items. So compared to the 34 and 18, we have much less items to have to get the 3-dimensional, have a high reliability from the multidimensional DCM. But there is a paradox in the DCM. Even if it increased the capacity to measure ability, multidimensionality, but the problem is we are sacrificing the fine-grained measurement of latent trait for only several categories. It means in the IRT sense, we can give a very specific number like, oh, your ability is 3.689 or minus 1.246, something like that. But in here, as I said, the latent traits are discrete, so we can give 0 or 1. We cannot give very specific number. So there is a paradox of the DCM. This is the path diagram when with the multiple latent variables. This is also the same with the previous slide, but the different thing is 2 attributes are interact each other. And as here you can see there is a line inside the latent traits. So we can tell the latent traits are discrete. And this Q matrix also showing this path diagram in matrix sense. So item number 1 is measuring addition and subtraction, but not the multiplication and the division. As you can see, there is a loading here, but there is no loading here. This is the respondent's profile or classes or attribute patterns, which is denoted with alpha C. C is a class. When the number of the attribute is A, then total profile that we can get is 2 to the A. Let's see how. When a class mastered attribute, then it will be attribute addition, then it will be 1. If they have not mastered, then it'll be 0. And subtraction also, they can get 0 or 1. Multiplication also 0 or 1. And division also 0 or 1. All 2 cases, and we multiply them, then it'll be 2 to the 4 is 16 profiles. Total profile is 16. So if we have A attributes, then the total profile that we can get is 2 to the A, 2 to the A. Let's see this respondent number 1. This person has mastered addition and subtraction, but not the multiplication and the division. And let's think about if this person has a high probability to correctly answering item 1 or not, or medium probability or low probability. This item number 1 is measuring addition and subtraction, And this person mastered addition and subtraction. And do you think this respondent have a high probability or medium probability or low probability to correctly answering item number 1? Medium, high? Item number 1 require addition and subtraction, and this person have mastered all of them. So I'll say high. Then what about number 2? This is measuring division, but the person has not mastered the division. Low, yeah, maybe low. What about item number 3? This one requires subtraction and division, and this one mastered subtraction, but not the division. Medium? Medium? That depends on actually your assumption and the models and which affect to the interaction terms. We'll see soon about that. As I said, the latent traits profiles and classes are 2 to the A, but that is very much to estimate. The estimates are like probability of assigning the class 1, probability to be assigned to class 2, probability to class assigned to 3. If we have 4 attributes, then we have 16 of this. And if we sum all of this, it is 1. So we don't need to estimate this one. So totally we have 15 parameters to estimate. We only have 4 attributes, but 16 parameters to estimate, 15 parameters, sorry. So we want to reduce that by using attribute hierarchies. If you see this graph, this addition is prerequisite of the multiplication. So this is 2 attribute case. So how many profiles are there? 2 to the 2, so totally 4. But if you see the profile number 3, addition is not mastered and multiplication is mastered. Is that possible? To master the multiplication, addition needs to be mastered. So this profile is not available in this sense.
Let's bring up a question. Hypothetical idea. Well, here's the thing. I would argue a student can do well with multiplication, not do well with addition, because they don't understand multiplication. They don't have to understand multiplication to do multiplication. I would argue as
about memory. Like memorizing multiplication.
Yes.
Yeah, absolutely. So that could be another attribute.
Yeah.
And so if it's neither of these, then you add another one that says memory or practice or something like that. Right. And try to control for this. No, I think what she's saying is so this hypothetical example is if you think about how we teach multiplication is bunching, adding by group, right? How many groups of 2, how many groups of 3. So a lot of times addition is a bedrock of how we teach it. But you're right, there are ways around it potentially as well too. But to the bigger picture, sorry to interrupt you. The nice thing is, so diagnostic models themselves in the field are an interesting field, but to the extent where they are useful, in part was a lot more fine-grained approach to what you're measuring. I feel like a lot of latent variable models, factor analysis, IRT will be like, oh, we're measuring happiness, or we're measuring, math, and they don't get to the fine-grained detail that you have here, like algorithmic operations on number problems, right? And so when you get to a lower level, you see that this type of feature, that different things may need to be precursors and so forth, and that may be a theory or testing. One last thing on this, when you ask me hierarchies, the next thing is, a lot of people think this is actually how you build curriculum, right? This has to come first, and then what this is laying out as a framework, the way that you can sort of test hypotheses, see if it truly is. But
my question is, could you design a test in which there is a correct answer? However, I know by mastered like these parts, so therefore I answer a different, well, I would answer this one instead of the correct one, getting like to differentiate that way.
You mean like so
like if you have like 2 plus 3 times 5. Okay. Maybe you don't know order of operations. And so you give an answer of 30.
Yeah.
Or whatever.
Yeah.
Okay. Now, you know, as the person who wrote the test, how they thought.
Okay.
So you said, well, I see that you know how to add and multiply. I can assign you these traits, but I can't give you the full. I know how to write order of operations, so I know how to add and multiply, but not that. Could you design a test like
yeah,
that?
order of operations with another dimension.
Yeah,
The item stock to measure it.
yeah.
Yeah, if you can manipulate. So the thought is anything that you can think of, and that is a really unique case. It's a logical conflict, like a logical language, right? So that works in ways that many other questions for other places are. But I think you have an example coming up, and I want to steal your thunder, about the DSM,
Yeah.
about pathological gambling. And if you think about it, this is an example that where right now it's like, if you think you have a problem with gambling, you call the number 1-800-BETS-OFF, and they give you questions like a depression screen, that's a gambling screen, how much do you think about gambling, blah, blah, blah. And you get over stuff and they're like, all right, go get help. Yeah, you got a problem. Something like that, right? But if you think about what the DSM is showing you, you've got much more fine-grained prescription. It's not a person has to actually, the definition of problem gambling is 5 of 10, to meet at least 5 or 10 different criteria. If you're trying to figure out what profile of those criteria are, because perhaps someone who steals money to gamble is a different person than someone who does otherwise, you can do something in this type of framework. And it's the idea that the trait itself is much more well-defined and narrowly focused. So the models that you're seeing here are great for it, but if you take this knowledge from DCM, you can also apply it to IRT or CFA, but also work in a little bit different aspects, but certainly DCMs do a really good job with it. And I know you're working up to it, so there's other parts of what they do that are a little different, but I'm not going to steal your thunder. Okay? I hope you don't mind me just adding a little bit of jumping in a little bit.
Please do.
Okay.
Yeah.
I should note, this is the area that I'm most well known for my research. I co-wrote a textbook on it.
I saw the references.
So like you'll see in the references are related to the work I'm doing, which is why you're like, why is Aiken doing it? Well, this is what you chose that you'd like to present. So I'm all supportive of it. But yes, I apologize for jumping in.
Please do. Yeah.
Aiken knows this very well. I would not trust her with this class if she did.
I forgot to mention this, but I made some slides, but I'll also use his slides he provided for me. So yeah, this not only about my materials and his materials also.
No problem.
And many things from books from him. Yeah.
So please continue. And it's I'll also just one last thing. Recognize the challenge she faces. She's trying to get teaching experience. Her advisor is sitting in the corner. Her course supervisor is sitting in the corner, and she's presenting on his research. This is a challenge. But I support her, and I think you're doing a great job. So please continue. Don't think that my interrupting is trying to correct what you're saying. I'm just more adding a little.
Yeah, I don't want to misunderstand. So I want you, if you can correct it, please do.
There's nothing to correct. Adding a bit more.
Okay, great. So we talk about this hierarchy, and there are several more types of hierarchies. So this attribute 1 is prerequisite of the attribute 2, and 2 is prerequisite of the third one, and third one is prerequisite of the attribute 4. So as you can see, the profiles should be 2 to the 4. It was 16, but now there is only 4 profiles. So the dependent each attributes make the profiles less, and we can see in the conversion type also. This attribute 2 and attribute 3 require attribute 1 to be mastered before mastering attribute 2 and 3, but they are independent each other, conditioning the attribute 1. So the attribute 2 and 3 are depending, 3 is depending on the attribute 2 here. So now we have 5 profiles. So it's less dependent, so we have more profiles. So if we, assuming there are more dependent on the attributes, then we will have less profiles to estimate. Yeah.
So when I first saw your convergent model, it appeared to me that you could go either through A or A2 or A3 to get to a mastery of A4. Based off your profile, you're indicating you have to do both. And so my question is, how would you write this sort of a model that would show A sub 2 or A sub either or to get to that and not have to have both?
Do you mean how do I specify this graph?
Yeah, how would you write that graph that would specify either way you can get to 4? You don't have to have both of those to achieve 4.
Before the test, we specify this matrix or this path diagram after discussing through the experts. The experts who are experts of the math test, they talk about this and attribute 1 addition is required to multiplication and division. They're talking about this and design this matrix.
And maybe I'm not phrasing this correctly. Go ahead. I'll think about a different way to rephrase my question.
Okay, sorry.
That's okay.
Then we can think more different types, divergent types. So attribute 3 and 2 is still independent and 4 is independent with the attribute 2. So we have more profiles to estimate. Now we have 6 profiles. And in unstructured way, the attribute 2, 3, 4 are all independent. So now we have 8 profiles to estimate. So when attributes are depending on each other, then we have less profile to estimate. This is the way we can get the reduced Q matrix through the matrix multiplication. If you follow the first, second, third, this process, then you can get the reduced Q matrix, because when we have more than 4 attributes, like 10 attributes, then it will be hard to specify the Q matrix manually. So we can get the Q matrix through this process. Let me skip this one. And if you want to review this, and if you have any questions, and you can ask me. Now we will start the measurement model part. The DCM is composed of 2 different parts: measurement component part and the structure component part. And we will talk about the measurement part here. DCM is a constrained latent class model. In the latent class model, they don't fix the number of the classes. But as we talked about before, if we have A attributes, we have 2 to the A profiles. So that number is fixed. So we already specified the number of the classes. That's why we say it's constrained latent class model. And in the latent class model, it's also composed of structure component and the measurement component. And this measurement component is showing the relation between the item responses and the latent traits. This is product of conditional item response probability. The conditional means it's conditioning on the class. So each class has different probability to correctly answering item. So you can see in this item, it has different, it also have notation C. So this probability will be different depending on the class. And the responses on each item are all independent. So we combine them with the product. And also this structure component is independent with the measurement component part. So they are connected with product multiplication. So we model the observed data with structural component part and the measurement component part. And let's see what's measurement components. One of the model is log linear cognitive diagnosis model. And it's a special case of log linear model with latent classes. And it also a special case of general diagnostic model. This one can model the graded order responses, but we're focusing on binary data. That is log linear cognitive diagnostic model, LCDM. So we define that binary data with a logit of a probability of a correct response as a linear function of the attributes. So on the left-hand side, which is observed data part, we use logit of the Y, and the right-hand side will be attributes will be connected to each other. And in the LCD model, there are two assumptions, compensatory model and non-compensatory model. This is an assumption under the model. And it can be used, it can be estimated through the N+. And the LCDM doesn't need a two-stage approaches for lining up and cutting. As we said, we don't need a standard setting to cut the, to get a cut score to divide people into two different parts. So after the LCDM, we can get the discrete latent variable and give that kind of information. This is the specific of the item response function of the LCDM. We take the logit of the responses, and it's composed of this intercept and H part. And let's see what this H means detailed in here. This is the intercept, represent the log odds of a correct response for an examinee in the reference group who has not mastered any of the attributes. So these terms, which related to attributes, will be 0 and eliminated. So this is the only left term. So this can be logit who has not mastered any of the attributes. So that can be a guessing parameter. And main effect means increase the log odds of a correct response given mastery of each respective attributes. So if we have 4 attributes, then we have 4 main effects. And this third purple box is two-way interaction between 2 attributes allow the log odds of a correct response to change given an examiner mastery of both attributes. This dot showing that 3-way interaction and 4-way interaction if we have 3 attributes and 4 attributes. This lambda is that you just saw here. It can be intercept, main effect, and 2-way interaction, depending on this E. If E is 0, and it means intercept. If it is 1, it's main effect. If it is 2, it's 2-way interaction. 3 is 3-way interaction. And this A show A is attribute to which the effect applies. So for example, main effect of attribute 1, then it will be like this. Main effect of attribute 2 will be denoted as this. And interaction effect between attribute 1 and 2, and it will be denoted as like this. Let's see the example of LCDM. This graph shows that this item is measuring addition and subtraction. And there is an interaction between 2 attributes. And we have 4 classes. One class which has mastered none of the attributes. We plug this 0 into the equation here. So this part, this is the main effect of the attribute 1. And we as this class has not mastered the attribute 1, so we plug 0 here. So it'll be 0. And this is the Q part. This item is measuring attribute 1, so it'll be 1. This is the main effect for the attribute 2, because this class has not mastered the second attribute, so it will be 0. And this item is measuring the second attribute, so it's 1. We do the same thing to all the classes and other interaction terms. Then we'll get the logit, -2 logit and -1 logit for class 0, 1, and the 0 who has a profile 1, 0, and 1 for the class who has 1, 1. And we can transfer this to probability, because if this is -2, and we know this probability will be 0.12. So if you see this bar graph logit response function, it's going up because this classes have mastered more than here. So it's going up, and this probably also going up. Let's see an example when there is a less extreme interaction. Extreme interactions are unlikely in practice. And this shows the positive interaction and the positive main effect. So if you see the equation here, we have intercept and the main effects and one interaction effect. And as this line will be cross each other, so we can tell, oh, there is an interaction. And also, if you see this 0, 0 class, it has a probability of 0.12, and 0, 1 class, the probability is around here, and 1, 0 class are probably here, and this 1, 1 class has very high probability. It is higher than just summing all of these 3 intercept and main effects, because we have this. So it will be larger than just summing all of these 3. Let's see the subsumed model of the LCDM, because LCDM was a general model, so we can specify other subsumed model by constraining other parameters. The GDM and LCDM has been a fairly recent, and other earlier DCM are still used. Such DCM like DINA, DINO, serum model are much more restrictive than the LCDM, and it's anticipated that the field will adapt to more general forms. Each of the subsumed model can be fit using the LCDM, fixing certain model parameters. And you can see the detail in this reference. We have picked 6 other DCM, and that is DINA, NIDA, ROM, DINO, NIDO, serum model. And we can specify them under the LCDM sense. These models can be divided into 2 depending on the assumption. One is non-compensatory model, and the other 3 is compensatory model. Non-compensatory model means a low value on one attribute, one latent variable cannot be compensated for by a high value on another latent variable. It means one latent variable, if attribute 1 equals 0, cannot be compensated by high value of another latent trait. Even if we mastered the second attribute, it does not contribute to increase in the logit or probability, because it cannot compensate the lack of the attribute 1. But in compensatory model, it can compensate it. The attribute 1, even if it's not mastered, it can be compensated by the attribute 2. One of the compensatory model is serum. Let's see the detail of the compensatory model. In this serum model, does not assume the interaction model. So if you see the equation here, there is an interaction term and main effect, but there is no interaction term. So as you can see in the logit line here, there is no interaction because they are not crossing each other and they're parallel each other. So before, when there is a less extreme interaction, it was higher than now, but as we don't have interaction term, it's around 0.7. When we had an interaction term, it was around 0.9. Now we have around 0.7. Let's see the DINA model, which is a non-compensatory model. It shows a conjunctive model. It means a non-compensatory model, but in different way. I skipped to explain about why it's conjunctive, but the DINA model is non-compensatory model. And this DINA model has a positive interaction and over additive logit model. So we assume by incorporating the interaction term, it can be an additive logit model. And highest interaction parameter is non-zero. It means when we have 3 attributes, there is two-way interaction and three-way interaction, but this DINA model doesn't assuming two-way interaction. It only remains the highest interaction, which is three-way interaction. And all main effects are 0. So if you see the equation here, there is only two-way interaction term, no main effects. So if you see the probability here, and when class 0, 0, their probability is around 0.1. Even if this class master attribute 2, this probability is still 0.1. And also 1, 0 profile, even if this profile class mastered the attribute 1, its probability is still 0.1. But if you mastered one attribute 1 and 2 both, then now it has a high probability. Did you get what it means? The compensatory and non-compensatory mean? Yeah.
Same thing works in linear models with interactions. Right? They're not. So this form for this model, even though a bunch of crazy notation, crazy equations, it's latent variable and open. That's really how to think of it. All right. So the attributes are demi-coded. And so therefore, in regular analysis of variance, when you have a factorial analysis of variance and all factors have crossed, that is what you see here. Actually going back to her attribute hierarchy slide of the method I built the nested model. When you have nested factors in an open, that's an attribute hierarchy in some sense. Or strict hierarchy, I'll come to know it as this.
I have a question that you might not be able to answer, but you might be able to answer. So when studying both linear models and generalized linear models, if you had an interaction term, you also, I was told thou shalt add the non-interaction term in your model. That's,
yeah.
That's not happening.
Were you going to say that?
And so my question is, okay, are we saying that we are assuming 0, therefore they're not needed, or what's going on?
Do you want to try to answer, or do you want me?
Please.
Okay. So this is the fun thing about this model, and the term that you see here, sort of, if you go into the diagnostic model literature, you can hear people talking about all these acronym models. They're everywhere. I've contributed a few. My bad. What the LCDM did was take a model form that looks like a linear model or an IRT model, and it showed how it made it related to all these other models that didn't have that form. And in doing that, that's what we discovered. The DINA model has an intercept and the highest level interaction, and all the lower order interactions and main effects are 0. That's a problem in data. So let me ask you a question. Why an analysis of variance would you need the main effects when you have an interaction? This is a complicated question. It took me many years to figure this out.
Well, honestly, it's depending upon what you're looking at.
No, it's a basic regression idea. If you don't have the main effects in, That means that interaction regression weight can be non-zero, right, for one of at least 3 reasons. Okay. All right. One is it's truly an interaction. Again, that's great. It will also be significant if one of the main effects would have been significant, but the interaction wasn't. Right? Yeah. And so that's main effect 1, but not main effect 2, and then there's main effect 2, but not main effect 1. I guess technically there's both of the main effects. So if you think of all the ways it can be significant, when you omit the main effects, you're no longer taking the interaction and controlling for the presence of those other variables, which are the main. Like in regression, when you think about omitted variable bias, right? You think, oh, I'm predicting Y with X, but if I omit Z, I have a bias of my prediction because Z is related to both X and Y, right? Right. So when I include Z, the effect of X changes. Right. Right. Main effects are omitted variable. Without that variable, it's omitted variable bias. What you get. That's simply it. So when you estimate this model, and I would say still, some 16 years after the LCDM paper came out, people use the DNO model more than they don't. What you get, you run the risk of thinking that truly more than one, the item measured more than one dimension, that interaction being present, when really it only measures one of those dimensions. And you can show a whole bunch of other effects from it too, bias of classification, bias for the parameters as well. Hierarchical weight set. And then they have a higher order trade as well. In this case, this is the measurement model itself. So these would just be the latent traits. And when she's done and I get to talk, I'll talk about the higher order model. So it turns out in this as a measurement model, each of these latent traits can also fit under a hierarchical or higher order model as well too. But we just haven't gotten to that point. I don't think you have that on your slides. But I think actually you do at the very end. So again, do you mind if we take a 10-minute break?
Yep.
Okay. I'll pause the recording and then take 10 minutes.
Yeah, we talked about the DINA model. And let's talk about DINO model. Oh.
You're welcome to say like and subscribe if you'd like as well. And if you have a YouTube channel, we can make this full out and link it. We used to not debate the merits of doing that, like the collab, where we combine forces in our channel. Not that the thousands of people that know us will know, but yeah, we should do that. We should make it like a podcast. I think we can call it office hours. Sit around. Anyway. Ae Kyong, you're welcome to collab. Yeah, but I gotta get rid of the merch. Yeah. Do that. Keep forgetting me. Okay, as you want.
Now let's see about the DINO model. This is a disjunctive model and it's also compensatory model, but the disjunctive is different way to say compensatory model. It has different way to explain that, but let's say we're just compensatory model. It has a negative interaction, so it's under additive logit model, and all main effects are equal. So if you see the equation here, this main effect for the attribute 1, main effect for the attribute 2 look same. And the interaction is still same as this main effect. Yeah.
Is lambda not allowed to be negative?
Which lambda? This is minus lambda.
Well, I
it should be,
that,
yeah.
Are they allowed to have a negative value?
No, it should be positive.
So main effects. I'm just talking about any effect of them. Do they have a negative value when you compute?
Lambda I cannot be negative in this case. Lambda 1. Lambda 0 can be any. And I think the slide Y is coming up in a couple slides.
Oh, okay, sorry.
Right? You haven't got this one.
I don't have the monitors here. Yeah.
Sorry, I'm so used to these being my slides, I usually put it right.
Sorry, I didn't mean to throw you off. It's just because I guess like it's a very and like where are we getting information?
So let me go a little bit. Can I go? Would you like to talk about monetization?
Please go.
Okay.
Yeah.
So this classic model, you did put up the slide that had the latent class model likelihood, which is a crazy looking long. Okay, that's just this is a latent class model, a mixture model. The problem with mixture models is they're used mostly to go figure out nominal type latent variables. So you think about what we're doing here in this slide. Up to this point in our class, we had continuous data and continuous latent variable that's IoT. Then we had discrete data, factor analysis. We had discrete data and a continuous latent variable that's IoT. And now we have discrete data and discrete latent variable DCM. Technically, we can lump the continuous data, but everybody has it, so we just follow that. So in this sense, with this being a mixture model, it's a new class. It sort of treats the type of latent variable not as continuous, but it actually treats it as just discrete and categorical a nominal variable. So when people typically use latent class analysis is to figure out, I'm like thinking it's like a cluster analysis. How many groups of people do I have in my data? It uses a probabilistic clustering method used based on whatever your model happens to be. And that latent class analysis, because the groups are labeled, you can fit an analysis and the output comes, group 1 is this, group 2 is that. But if you randomly permute the starting values, group 1 may be group 2 in a second. Basically, you can permute the labels, right? Well, to make this, the attributes, latent variable and model are a little bit different in that they're not nominal. They're not things that we don't know. And there's two categories. The zero category, what we're calling non-master, has less of the trait than higher categories. So technically, this is a type of data that isn't nominal and that isn't continuous. So it's a latent variable, it's an ordinal latent variable. And so to make that ordinality whole, we have to put in with something called a monotidicity constraint. Basically, we have to go and we have to basically hardwire in the latent class model a catch such that, well, basically the idea being that the more attributes a person has mastered, the higher chance they'll answer an item correct in an educational sense. It's different for it's the same for the cognitive. The more, so basically we order people by how many they've had. Those the math for that works out so that all the main effects have to be positive for that to be true. But then the interaction has a lower bound than some linear combination of the lowest main effects. So as you get to all the interactions, the intercept's never bounded, the main effects are always bounded below by 0, and all the interactions have a bound, but that depends on the lower order terms as well. And that enforces monotonicity to allow us to make some claims about the groups of people that have. This is sort of the psychometric engineering you need to take to map this version of a latent variable model on the latent class architecture. It's a long way of answering your question, but the question brings up a topic that's really like Ae Kyong's giving a half of a lecture on this, and I've given semester long courses, right? So this would be a topic that we would have in such a course. Thank you. You're welcome.
Now let's start the structure model, which is another part in the DCM. The structure model is modeling the attributes spaces. So it shows the relation between attributes, multiple attributes. So for a test measuring A attributes, we totally have 2 to the A profiles. So the structure model provides the probability of each profile. So if we have a probability of assigning to the class 1 is like this, and we have the probability to be assigned to class 2, and if we have 16 classes, then we all have this probability. And these are called also base rates. And based on this probability, we can get the information proportion of masters of any given attribute. And also correlation between attributes. We'll see how it works. This is unstructured structure model. So as we said, we have 4 attributes. So now we have 16 classes, and each class has a probability. So we can say 21% of examinees are assigning the class 1. And class 2 has 7%. So totally we have 16 class, each proportion of each classes. And what information, this is the output after we estimate the model. And what other information we can get is marginal base rate. It means the proportion of examinees who has mastered attribute 1, attribute 2, attribute 3, and 4. How can we get it? We sum all of this proportion who has mastered attribute 1, all of this number where the class has mastered attribute 1, then it will be 0.31. And if I sum all of this green box and pink box, then it will be 0.55. Then what kind of information can we get? This attribute 1, there is 31% of the people have mastered attribute 1. And this attribute 3, there is 63% of the people has mastered. Then we might get information that attribute 1 is harder to get. And also we can get pairwise estimate. This has the same logic to get this number. Can you guess how can we get this 0.422? This is attribute 1 equals 0, attribute 2 equals 0.
How about the top 4? Because that's where both ones have no 0 attribute for a case of 1 is 2.
Yeah, that is correct. So we sum all of these four classes probability because they has not mastered any of these 2 attributes. So we can get this 0.422. And also other numbers can get from the same process. And the other information that we can get is tetrachord correlation. If we put this contingency table into the R and use the site package and the tetrachord function, then we can get the tetrachord correlation between these 2 attributes. Tetrachord correlation is correlation between 2 binary variables, assuming underlying them, they are continuous actually. We'll talk about this. In here, what we can get is we can get tetrachord correlation based on the contingency table. So this attribute 1 and 2 has 2 correlations are 0.78. Because there are numerous epsilon parameter, we have 16 parameter, actually 16 minus 1, 15 parameters to estimate. So it's a lot. And it is same as saturated model. So we want to reduce the number of the parameters by using the categorical data analysis technique because we're assuming the attributes are binary. So let's see how, what kind of models we can use. One is log linear model, tetrachord correlation model, hierarchical model, and mixture model. And in here, we are going to focus on log linear model and tetrachord correlation model. Let's see the log linear model. We're modeling the epsilon C after taking the log. So we're modeling with this mu C instead of epsilon C. This re-expression on the log scale is convenient as these terms can now be modeled by other features in the model. So we modeling this mu C with attributes relationships. By simplifying the estimation, we can reduce the number of the parameter to estimate total number is 2 to the a minus 1, but we can reduce it using this log linear model. Because we take the log from the epsilon c's, so we will go back to here using these equations. In the n plus, it fixed the value of the last class mean to 0, and we'll see how it works. This is the log linear model. We are modeling this mu c, which is a log epsilon c. This equation is very familiar to you because it's similar with the log linear LCDM model. This is the main effect of attribute. This is two-way interaction effect between two attributes. So if it is 1, then it's main effect. If it is 2, it's two-way interaction. In the profile number 1, attribute 1, this class 1 has a profile 0, 0, 0, 0. So we plug this all 0 into this model. And then this term, all the term will be eliminated. So mu1 equals 0. So that's why we have 15 parameters to estimate, because this one is fixed to 0. Let's see the profile 6. Its profile is 0, 1, 0, 1. So these purple boxes remained after we eliminating all other terms. So this mu6 is left equals gamma 1, 2, gamma 1, 4, gamma 2, 2, 4. If you count all of this gamma, that is 15 parameters to estimate. But if some parameters are significantly not different with 0, then we can remove that. So we don't have to estimate that parameter. That's why we can reduce the number of the parameter here. So when there is no main effect and no interaction, then all attribute profiles are equally likely, because there's no relation between all attributes. And if we only have main effect and no interaction, then it means there is no correlation between attributes. And main effects are essentially equal to the attribute base rate. And if there are main effect and interaction, then it is statistically equivalent to saturated structure model, because we couldn't reduce the number of the parameters. Now let's see the tetrachord correlation model and structure model. The tetrachord correlation is a measure of association between two binary variables. And two correlation comes from mapping binary variables onto two underlying continuous variables. If you see this graph, the value that we can see is 0 or 1, which is binary, but we're assuming they're actually continuous. So we denote it with alpha tilde. By this threshold or tau, we can separate this number into two different parts, 0 or 1. So after estimating, we can get the parameter tau. And because we are assuming there is a correlation between the attribute 1 and 2, so there is we want to get the correlation between these two attributes. So after estimation, we will get tau of attribute 1, tau of attribute 2, and a correlation. This is the detail of the tetrachord correlation. This is a contingency table that we saw before. And underlying them, there is these two attributes is distributed like this. And based on the threshold 1 and threshold 2, let's focus on the threshold 1. Threshold 1, we can say there are this amount of people. That's what we saw in here. Let's say it's around 0.7. Based on this threshold, we can divide this attribute into two different parts, and the result is the 0.7. And the other part will be around 0.3. That's here. And also the attribute 2, we also have a tau 2, which is a threshold. So we can get this contingency table. This is the multivariate attribute case and represented with equations. But the thing we need to focus is we want to get the tetrachoric correlation between each pair of the attributes. So let's say there are 3 attributes. Because it's correlation, so variance are fixed to 1, and we want to find the correlation between 1 and 2, correlation between 1 and 3, correlation between 2 and 3. That is a tetrachoric matrix. And also, before we said we need to estimate the threshold. So we will get a threshold for each attribute. So 3 threshold. That was unstructured tetrachoric model. Each attributes, we know they are correlated each other. So we want to find the correlation between all pair of the attributes. That's how we get the parameters. In this unstructured tetrachoric model, we have 4 attributes. So there are 4 thresholds to estimate, and there are 6 correlations. So totally we have 10 parameters to estimate. But that is still a lot for us. So we want to reduce that by structured tetrachoric model. Because if they are highly correlated each other, we can assume that there is a higher order factor. So you might be familiar with this equation because we saw it as, just skip it. Yeah. So yeah, tattoo is here. Because they're, yeah.
Sorry, with equations like this, they just go on forever, they seem like, right? There's tons of them. So you start to see forms of it. So you're like, oh, something different, something the same with the T. Okay, I've seen that one before. So yeah, but I do think that factor analysis and path analysis in particular, the matrices become like there's certain products and things that you end up getting where you just start embedding the same thing. And the length of the equation looks like German words. I don't know, like the German nouns where they put different nouns together and you get a 40-letter word.
But this is Greek now, Greek word. Because
this is Greek characters, yeah.
So that's the previous guy.
It's a whole lot of stuff, yeah.
Yeah, so we can assume that there is one higher order factor when we can, and then we can model the attributes. So in this unstructured tetrachoric model, we have 6 parameters to estimate tetrachoric correlation, but now we have 4 loadings, so we can reduce it 6 to 4. So totally we have 8 parameters to estimate. So we reduce the number of the parameters. And this is the example of the DSM, which is a criteria diagnosing for the mental disorders. So these are the criteria, and there are 10 criteria or 10 attributes. And these criteria are all related to dependencies. So we can assume that there is a 1 factor dependence, and these 5 factors or 5 attributes are related to this disruption. And these 3 are related to loss of control. So we reduce this 10 relationship with using this model. So now we have 10 latent thresholds because each criteria will have the threshold. Now we have 12 factor loadings because 2 criteria are measuring 2 attributes, 2 factors. So 10 plus 2, we have total 12 factor loadings. And these higher order factors are correlated each other. 1, 2, 3. We have 3 correlations. So totally, we have only 25 parameters to estimate. This is very much reduced from the unstructured tetrachoric structure model. In unstructured tetrachoric structure model, we have to estimate all the pairs correlations. So it was 45 plus 10 thresholds. So we had to estimate 55 parameters, but now we have 25. And if we don't even model with the tetrachoric model, then if it was unstructured structure model, then it was 2 to the 10 minus 1. So totally we had 1,023. So we don't want to estimate this amount of parameters. So we want to reduce it this much using the structure model. So let's summarize today's class. DCMs are a family of statistical model designed to analyze discrete item responses and discrete latent variables. And the reliability of the DCMs are high with multiple latent variables, sacrificing continuous measurement because we can't give only 0 or 1 data after estimating the model. And the LCDM is a general measurement model of DCM, subsuming other models like DINA model, DINO, serum model that we saw before by constraining the parameters in the LCDM. So DINA model only has an interaction term. It doesn't, we're constraining the main effect to be 0. And structure model is an essential component modeling the attribute spaces. So we show the relation between attributes. It was not related to items. And through the structure model, we could reduce the total number of the parameters. So it was 1,023 to 25. That's all I prepared today. And thank you for listening. I really appreciate to give me this opportunity. Thank you.
Questions? Thoughts? You don't usually see this type of lecture in the structural equation model class, but you see how it fits in the bigger picture. The type of measurement model. As I mentioned when we got the factor analysis, I said, well, actually, I'll save that for my next lecture. Yeah, so you see how it fits. It's a different type of measurement model, but it still fits within the whole framework in ways. And, I think these are interesting models. They were they're still fairly popular research-wise in the psychometric world, but you can see very limited application of them in places. I think people are much more excited about, can we use AI to do like everything these days? Whereas like the modeling work, whatever. Anyway, that's my way of saying they're popular, but I'd say they're not as popular as they used to be. And then more recent research we've done, right, that talks about what the cut point is, what the fine for that is. We've got some ideas on how to do this better, so we're going to refine that. Ae Kyong is going to help change the DCM world in this few years. Thank you. Other questions? All right, Ae Kyong, thank you very much.
All right, so now let's talk about higher order and method factor models. But the bigger picture is this. I want to put this into the context of our variable. You remember our course so far. So remember that very first example I had, which was we were measuring happiness. I'll just put an H there. We had 5 observed variables right here. And X5. Sorry for the time it takes. And so this was our measurement model for happiness. And basically, we took marital status and we predicted happiness with marital status. That sound right? And so if you think about the beginning of the class, we did this in the not so elegant way where we had marital status predict the sum of all the items. right here, which we called happiness, right? So we swapped out this. So we started with path analysis. And then we moved and we said, oh, no, we better do a better job here. So we made it a measurement model right here. So this part up to this part right here was a measurement model. I'll call that measurement model or factor analysis, right? Maybe confirmatory factor analysis. And then we found out, oh, we should probably really be doing IRT there, right there, right? And then when I talked about in that concept, when we put the path analysis back, so this part is still path analysis, right? Right here, this part, when you put back together, when you have a path analysis and a measurement model, you get structural equation model, right? So that's, again, refocusing what we're thinking about. The other interesting thing about that is if you had only, if you think about it from the perspective of what you were trying to achieve under the path analysis with the sum, we created a new variable. We called this thing in this circle happiness. I'll call it H star, right? And we're predicting it. We put it in a path model, right? But the measurement model basically served to build exactly that H, where H star was. So what I'm saying with that is a measurement model you can think of as a definitional model to define a variable that will go into path analysis, but do so in a way that you don't have to actually make multiple steps. Does that make sense? Right? And so once you define the measurement model and you get, or you define H, right? Now it's treated like it would be in any other bit of code. So case in point, what I'm saying that is, if we were writing Lavon code, right? This first model right here, I would call this, we would have, it would just look like this, HS for star, right? Tilde marital status, right? So that's our first model there. The second model would be a little bit more complicated, right? We would define happiness, which is just H, with an equal tilde, and we would have X1, X2, X3, X4, X5, right? As separated by pluses. But once we defined H, when we get down to this next equation for it, we treat it like it's a variable in our data set, right? It's a variable in our data set. We would just say, oh, H is being predicted by M, right? So the measurement model step, what I'm getting you to think about is the measurement model step, whenever you see an equal tilde right there, it's like you're defining something that doesn't exist. But once it's defined, you treat it like it existed. Get me? In Lavon, it doesn't matter, no. But I'm putting it, I'm doing it this way conceptually to say we need to define it before we use it. Yes. Yeah. Question. Can I? Oh. We're getting there. We're going to get there. I promise. All right. So let's imagine, though, that you said, actually, no, that's the old version of happiness. I've got a new version. All right? I've got three things that talk about happiness. I've got happiness when it comes to money. I don't know. Happiness when it comes to social skills or something like that. And maybe happiness when it comes to health. I'm making things up, okay? Again, these things are measured by observed variables, right? So you may have, at least three on each. I don't know what those variables are. But once you've built them, now this is where the hierarchy comes in, right? What you can say is, okay, so my three variables, even though I define them, again, X1, just the lack of boxes, don't let the lack of boxes fool you. The boxes are there, you have to observe them. What you may now say, what's that? Yeah, you just can't, you could create a model in Bayes at least where you're just simulating data. It won't get you very far, but you could do it, right? What I'm saying here is these are three factors. We have to pretend, if we pretend that we measured them, come on, where are you? These three things right here are factors. So if we pretend they're measured, let's think about them for a second. They are continuous. Like we define them to be somewhere on the real number line. So, before we had to worry about types of data and stuff, like if we were to model these, what I'm getting at is there's nothing stopping us from saying these three versions of happiness might define an overall happiness that looks like this, right? And this is what we sometimes call a hierarchical model, sometimes we call a higher order model. But thinking of it this way, had we observed three versions of happiness that we just measured, we could put all three of those into a factor analysis. So a hierarchical or a higher order model is a factor analysis on factors. And then we could then take marital happiness and predict it with it. Yes. Okay. Yeah. I don't, but yeah. Yeah. So what I'm getting at, and question about the hierarchical. This is what I'm calling hierarchical. Is that with what you were asking me about? Does that seem okay? Good. Good. Right. So sometimes we hear the term hierarchical when it comes to multi-level models, hierarchical nesting structures. Sometimes we hear hierarchical when it comes to Bayesian modeling, where you may have like parameters that have empirical distributions that you're estimating as well. So the term, when you asked about the question about hierarchical, I wanted to make sure we defined it first, because hierarchical things means many things to many in many different fields, and actually many things in this field. So good question. Yeah. Yes. So yes, that's it. Basically, I'm giving you the lecture before the lecture here. All right. I'm lecturing with a chalk, like an Apple pencil rather than a piece of chalk. But that's what I'm trying to say here. So just like a factor analysis, we have to remember that there are at least three indicators of this higher order factor. Now, those three indicators are lower order factors. We didn't observe them, but we defined them. So backing up for why I'm doing this drawing, I started here to say that once we define a latent variable, it's like we've observed it and we treat it like that. A higher order or hierarchical factor model does that. It says, oh, remember those factors? Let's put a CFA on it. Does that make sense? Yeah. And then if you want to go really crazy, right? This hierarchical structure appears in many places. So there's a field of measurement models called multi-level structural equation models, multi-level measurement models. If you'd like a course on that, Lisa and I taught one over the summer. There's a link to it on my website. We taught in Mannheim, Germany, for this class. So it was kind of a fun experience, very warm. But what that does is it says, okay, so your measurement model, each one of these items have an intercept. What if we take that intercept and say each item is not only nested within a person, but also in a group? So we come up with like a basically random intercept by group. So now we have 5 random intercepts. Can we factor analyze the random intercepts? That's a multi-level measurement model. But that's what I'm trying to say. So wherever there is a variable you've created, we can make a factor model out of it. And that's a whole bunch of the fields we have. Yes? Big. Probably not in the, well, I used to like to say, like when we got into the world of big data, this was like 2010 to 2015, people run around like robots talking about big data. Like if you collect your own data, it's big. It doesn't matter what sample size you have, 30 observations. But yeah, absolutely. You're going to have think about the number of clusters that you have, higher order units. The example we did this summer, we had, I think, 50 schools. We had students nested in 50 schools measuring 10 items of a math test, right? And so that example was really funny because, anyway, yes, you need a lot of data. But the point I'm trying to make is when I taught you CFA, you will see factor analytic solutions everywhere if you allow it. So let me go a step further, because Angela, I know you talked about mixed models before. So I'm going to pull up a crazy thing. I'm going to grab the user manual of my favorite mixed model software, which is SAS ProcMix. Now, this is an older one, but it's still in there. SAS-proc mixed, if you have a random, like a hierarchical linear model, multi-level model, or mixed effects model, you end up having random or repeated measures, right? So you'll end up having variance components reflecting the randomness. Sometimes if they're random, like a random intercept, random slope, so forth, you'll create what's called the G matrix out of it. You may also look at an R matrix, which comes from repeated observations, autocorrelation terms, and so forth. Typically, the R matrix can be very large in how many variables it ends up getting. So you can specify a covariance structure, and wouldn't you know, there's a factor analytic covariance structure for it as well, too. And so what I'm trying to say is the factor analysis part, even though we're talking about it from a psychometric perspective, and we can arguably link this to Spearman 1904 in the field that we now call psychometrics, factor analytic structures show up in many different fields of what you do, and it just presupposes that the variables have some type of common root to them. So it shows up in places. So I see that look. Is that good or bad? No, yeah. I'm trying to connect fields to it. But more to our point today. So a hierarchical or higher order factor is a factor analysis among factors. That's it. And it turns out if you have enough of them, maybe we have 12 first order factors. Maybe we'd make 4 second order factors. You could make a third order factor. Right? You can keep doing hierarchies as much as you want. That's the purpose. That's what we do. So I'm going to dive into that. The slides are Lisa's slides. I even kept them in her blue just to make sure that nobody knew I put no effort into this. I'm just kidding. There was effort, but But so I'm going to cover a little bit of this now as we go forward. Okay? Actually, almost time for a break. Let me just pause here. I'll give this slide and I'll give it a break. So. The question higher order factor models is asking what kind of higher order factor structure best accounts for the covariance among the factors themselves. So remember how we talked about a factor model on observed variables. The factors should be variables that measure the same thing, right? If you have more than one factor, within factor, there's higher intervariable correlations than between. Same thing happens when we do a factor analysis of factors. The factors themselves, in the example that Ae Kyong had given, we had 3 higher order factors: disruption, dependence, loss of control, right? Those 3 higher order factors, we could have said all represent pathological gambling on top of that, even if we wanted to. But those 3 are separable. And actually, if you read the DSM, why each of those labels were there, those labels were literally in the description of the disorder in the DSM. It said individuals suffer, these 10 criteria map onto loosely 3 different areas, and that's how we had mapped those themselves. So the structural model, sometimes we call that the correlation matrix among factors, is the structural model itself. When you put a factor model on it, the one catch is you're reducing the number of parameters you have. Right? So if you think about this example right here is not a good one because we're not actually reducing it. Remember, we're 3 indicators. This area is just identified, so 0 degrees of freedom. But when you think about the number of parameters, why we do model fit tests is we basically have a saturated model, and then our factor model has fewer parameters than the saturated model. The same thing's going to be true here. We'll fit the model that's not higher order first, then we'll fit the higher order model, and it will then that not higher order model serves as the saturated model of our factor model. So it's just a few things to walk through as you go through. I'm going to walk through that when we get back from break. So let's take 10 minutes and have a great time. Rest those brains of yours. See if you can go factor analyze something in the hallway. Okay, so going back to this, the higher order model is an addition to the analysis. So the analysis process, once again, you fit your not higher order factor model first. You achieve good model fit, right? That not higher order factor model has a saturated correlation or covariance matrix among the factors. So that's your alternative model now when you apply your structural model to it, because it will reduce the number of parameters from it. So I'll show you in just an example in just a minute. I know the words are not coming through as easily for some reason. But so right here, let's see what we can do. There we go. Okay, so there are distinctions between we in our class this part you might hear, oh, okay, I have categorical data, so I'm going to use item response theory. That's the name of the measurement model. Or I've got continuous data. I'm going to assume continuous data, use the confirmatory factor analysis. When you get to the higher order model, in the case of continuous latent variables, there is no choice between these methodologies. They're all the same. It's all for continuous. You've defined a variable to be continuous, and that factor model on factors, this thing right here, these factors are all continuous. So this, by definition, is not only the right model, it's the only model you can use, because you can't use an IRT model with continuous indicators or variables. So the name itself of the higher order model is usually factor analysis. Now, I'm going to give a huge caveat that Lisa wouldn't put in her slides. She did teach DCMs once. It was like in her SCM class, it was like 2009. But that being said, there's like a slide. Okay. In DCMs, the traits are discrete. So the higher order model that would show up there is more like an IRT model, right? But that's not that important of a distinction. For most of what you will do in Lavon and everything you'll do in Lavon, they're all continuous. Okay? Okay. So when you do the higher order model, typically we want to use marker items to estimate the lower order factors. And the reason for that is, turns out the factor variance itself becomes important, right? Factor variance in a higher order model, the factor itself is going to be predicted by the higher order factor, which means that variance should shrink, right? Because now it's being predicted for. So what we want to do is we want to use a marker item. Now, you don't have to. There are ways that you can do it otherwise if you're okay with wholesale parameter changes. But once you, to identify your higher order model, by convention in most of the world of CFA, we will use a marker item model for all the lower order factors, the first order factors. By the way, those words, lower order, first order factors are referred, I use those terms to refer to what we called factors up until this week. The factors that touch the data, that are predicting the data itself. Okay. So you can come up with one version. So you know if we had three different factors, so this would be first order factors. They're all, here, I'll just use the mouse. We have a marker item for each, so each of the factor variances is estimated. The structural model up until this week would have the three different covariances between the factors, the three different variances of the factors, and then the mean vector here, because the mean, we didn't say anything about that. There is no mean vector, so the means have been fixed to 0. So this is marker item identification for the variance, but not the mean, okay? So that's one way of doing this. Another way of representing this would be the higher order factor itself, right? So once we put a higher order factor on this, now we have a higher order factor. We may identify it as a standardized factor itself, where the mean is 0, the variance is 1. Now, the leftover factor variances themselves are sometimes called disturbances, which I shouldn't have called that in my slides, but that's okay. The ones that we talked, this is a conversation we had. Those three variables, these disturbances are what's left over. Another term for disturbance is residual. These are residual variances. Why are they residual? Because if this path model holds, we're predicting each factor by this overall higher order factor itself. Does that make sense? Okay. So the difference between these two slides models is that actually they're equivalent. There are 6 possible parameters in the structural model of this correlated factors not hierarchical. 6 parameters estimated, that means our degrees of freedom would be 0 if we just look at the correlation matrix of these 3. Right? When we go here, again, we still have 6 possible parameters if we just look at the covariance or correlation matrix of the factors. But we have 3 loadings, and we have 3 residual variances. Right? So it's also just identified. So if you wanted to test whether there was one higher order factor or that we should have 3 separate factors, you can't do that unless you have a 4th factor itself. These 2 models are identical in terms of model fit. They're not identical in terms of what you get out of them, but they're identical for model fit. What do you think about that? Maybe you don't. Which covariances are you referring to? No, I don't think it's not preferable. I mean, you can usually estimate the covariance matrix between factors pretty easily. So it's not a parameter estimation issue. Most of the time, we'll turn this into correlations. We use that to determine how correlated 2 factors might be. So I don't know that that's it. I think it really drives from if you think there truly is a trait that you wish to measure that's indicated by low first order factors. That's where it comes from. I don't know why, of all the things to get through on my watch, it wants me to talk about how I'm feeling at this time of day every time I teach. And so just because I already made that note, because I'm talking about higher order models, I'm gonna note that I'm actually feeling quite very pleasant right now. There we go. You're now part of my collective data experience. And I'll work better to make sure that doesn't get through my block on all notifications for this class. Okay. Sorry. So you hear this weird vibration. And usually, so I try to knock down all notifications unless my kid's school or my wife calls, because it's usually someone's dying, right? Or someone needs emergency. So when it buzzes, I'm like, oh, tell me how you're feeling. Yes. I'm feeling great. All right. So if we do now, the last slide here, option 3 or option 2B, just takes our higher order factor, and instead of using it as a standardized variable, it's a marker item now. That's okay too, because the factor analysis works the same. You can identify it as a standardized factor or a marker item. Just because it's a higher order factor, we have to pick one, but we could do either. Yeah. Right here.
So does that mean that variance, it's going to go all the way up, it's going to follow it up to the top?
No, not necessarily.
So or is that going to be different when you go from F1S to our higher order factor?
So let's think of it this way. There's a variance for Y1S.
Yes.
The variance of F1 is a portion of that variance. So it does anchor the variance of the higher order. But what that portion is depends upon the size of the variance. And
The higher order is kind of a portion of F1S because of our...
that's it. Yes. Yeah. And actually, what you really want to think about is this one, where Y1 is the marker item for F1.
Yes.
So that's the variance. But now F1 is the marker for the higher order. Exactly. So eventually, this variance has an anchor for it that's Y1's. I call it an anchor, meaning it's sort of almost like a center point, right? If the variance of Y1 is bigger, you would expect these to be bigger, all things considered equal, right? The loadings and so forth being considered equal. So, that good? Okay. So, what if you have 4 lower order factors? This is from Brown's textbook. There's a problem-solving, cognitive restructuring, expressed emotions, and social support factor. Then you want a problem focus or an emotion focus. Right now, you can tell both of those higher order factors only has 2 defined indicators.
Isn't that what makes an
That's a problem.
where you have to define one of them?
Nope, let's talk about this real quick. Let's do the math. With 4 factors, how many parameters are in this structural model? And let's just look at the covariance matrix. Right? So we would have 4 variances, and then we would have 4 choose 2 or 6 covariances. So there'd be 10. Right? So here, the structural model, the degrees of freedom themselves, if we want to go count that, how many model parameters we'd have? We'd have 1, 2, 3, 4 residual or unique variances. And then we'd have 1, 2, 3, 4 factor loadings and 1 correlation. And, or that depends on how we define it, marker or otherwise. And what we end up with is an over-identified model with 1 degree of freedom, but it needs this thing to be estimated for it to be structurally identified. So it's getting to a part where I'd still want to have 3 or more indicators, is what I'm at. There are ways that you can form 4, higher order models with more, but I think 3 or more is better. This slide right here, if you go back to the CFA slides, is the identical slide that was then about the factor analysis itself. If you have, instead of replace measurement model factors with the word observed items or observed variables, indicators, right? The identification should be the same. So, how do we do this? How do we test? Now, the test is this. Remember, model fit's important. If we don't achieve good model fit of the not higher order, the first order model, then everything else is not going to work not well from beyond it. But let's talk about how this works. So you want to say, how do you get to say there is a higher order factor model there? The way you get to say it is you fit the higher order factor model, and if it fits as well as the model without the higher order factors, it says it fits the data, and there is a factor there. So let's talk through it. So the question would be, do I have a higher order factor of my subscales? So if you have 4 or more subscale factors, you can compare the fit of alternative models, right? It's no longer just identified, it's over-identified, right? You can have a hypothesis test, a literal hypothesis test for it, right? This would be a likelihood ratio test that you could use, the ANOVA function between the 2 models. If you have 3 or more subscale factors, you do not get to test, so you can't confirm statistically that the higher order factor is there. So it's tough because you're like, you could have a higher order factor with 3 variables, and it's perfectly correlated. That model, it's an identical model to not having the higher order. What I'm talking about is this model and this model are identical in terms of model fit. You cannot compare them, but one doesn't give you a higher order term and this one does. So I've been in many situations where people will use a higher order in this case, even though they can't test whether it's there, because it's synonymous with a model that's not. It's just an easier way of describing it. Okay. You may still have multiple higher order factors. So it's possible, although it's much harder to do, to fit a higher order model. Let's imagine we have, actually in the DCM example Ae Kyong gave, we had 10 lower order factors. We said that those all loaded onto one or more of 3 higher order factors, right? Well, it's possible that didn't fit. It's possible we could have only used 1 higher order factor, or it's possible we could have had to use 5 or 6. So you still are going to have to look for model fit of the higher order factors once you do the lower order factors. Does that make sense? So, okay. Whether or not you use higher order factors, whether or not higher order factors are useful depends on the context of the rest of the structural model. And of course, how correlated those examples are. So here is not that useful, right? You've got a predictor predicting a higher order factor where the lower order factor loadings are very, very high. What's this telling us, right? Just predict each one separately, right? Because the higher order factor, basically what you get out of this is the following. You're trying to summarize, basically you're saying, what's the impact of my predictor on each of my factors? Like, well, I don't want to summarize that. I just want to blend all my factors together to come up with this overall construct. Yeah, maybe that's important for your story, but what's more likely the case is there's a differential relationship of predictor on each of these factors. And with 3, it just makes a little bit of sense to predict it. But people do it. It's just not, I wouldn't say all that useful. This is more useful. I think this relates to what we were talking about during the break, right? You might have an outcome of interest, and you might want to take this higher order factor and predict the outcome. In this situation, this is a very interesting one in that look at the direction of the arrows from higher order factor. They're all in the same way. That means outcome is now part of your measurement model for the higher order factor, right? Which is kind of weird, but it does happen. This thing right here, very common, works very well. Was thinking about this earlier today with a different problem I'm working with. So going down to the bottom box, this is not that useful because look at those factor loadings, right? You've got very low relationship between factor 1 and factor 3 with the higher order, and a much higher relation between factor 2 and the factor order. What is that? It's not likely to do much to tell you. And then not useful at all. This is because instead of having one loading high, none of the loadings are very high. It means there's not a lot of correlation at all between the lower order factors. So if you can add them up, you can always add numbers up, or you can put them into, but there's just not a lot of value to it. Is right. This is a picture from one of Lisa's papers where you would have, let's see if I can talk about this here. You've got, what's that? What was it? What was the class in spring she put this in? Generalized. So she had this for path models. All right. Yeah. So you got a visual impairment factor. You got a processing speed factor. You've got driving impairment right here. Each of these is predicting output from various tests itself. You've got age that also predicts some of this as well. And this right here is where, I'm glad she highlighted this. If I remember correctly in her dissertation, she said, someone said you need a latent variable for these three things, and she disagreed with him. And so, and I'm not going to name the names, but I know the guy. It's consistent. It checks out. Sort of fits the pattern of behavior. But it reinforces what I say. Wherever there's numbers involved, there's someone going, can I put them in a factor analysis? Can I put them in a factor analysis? Anyway, what this would have done is you wouldn't have been able to tease out the differential impact of age or visual impairment or driving impairment on each of these variables. So sometimes a higher order factor, what this is trying to say, sometimes a higher order factor is really not all that helpful. Right? It depends on the story you're trying to tell. Now, okay, this set of tasks, I'm going to give the counterpoint to it, right? If you're dealing with somebody who is not a scientist, not a quantitative scientist, and certainly not someone who's into psychometrics, showing them this picture, I think, what did you say when I put this up? Oh, wow. Yeah. That's what you're going to get. If you want to try to communicate this information, it may make more sense communicatively to lump those into a factor and describe it. Because then you can say, what is the impact of, driving impairment on attention, or the other way around, attention on driving impairment, right? Rather than saying, what is this version of attention on it? So it may make sense depending on who you're talking to. And I can certainly tell you the people who are trying to do better job at training drivers or trying to make sure that works, they may not understand the nuance that's here. So there may be other reasons that are not statistical to do it. Anyway, questions?
So, yeah, that's working with higher order factors, more exploratory than confirmatory.
Not always, no.
Okay.
Yeah.
Because try to see if it's there versus, that's the goal.
That's it.
That's it.
That's it. Yeah, no, it's not at all that. I think higher order factors make a lot of sense in a lot of cases. I mean, I use them. I measure all these how students are doing on various academic standards at various parts of the year. I'm measuring at the standard level, but let's say they're all math standards. It's valuable to me to know if the math standards, how they load it into a higher order model. Turns out they load actually quite well. The model fits very well. The standards all work together very well. They're not unidimensional. Another thing is to have a unidimensional higher order model does not mean you have a unidimensional set of data. So, like in my case, it just makes sense. I'm like, oh, this is how we do a lot of assessment. We build items based on standards, but we give scores based on the higher order, but we never do the analysis in between. So, questions? Any other questions? All right. Okay, so let's do some reconsidering of item construction. This is, I think, where we're starting to pivot into other ideas about how we can build more factors to control for things. So latent variable measurement models can represent multiple underlying constructs, but only to the extent that items in their design could distinguish them, right? Because the factor doesn't exist. It depends on the items. So it's not higher order factor. Let's just think regular order. And if the items aren't written well and you just get random responses effectively, you will not have a factor model, right? So there are some general principles from item design that you know about from survey measurement research. Items should cover a single concept with a single explicitly defined referent. That is an old one. That's for the higher order ones. If you're in DCM world, you can get to much more of that. That's okay. You should provide response options that are applicable to all respondents. I was just filling out a survey the other day, and it was like, "Why are you, leaving our service?" And then why I left was never one of the options, and there was no other. I'm like, oh, I guess I'm not going to tell you, right? Anyway, items themselves don't want to be too narrowly defined, not too broad. It's very difficult. And then there's general principles for measuring multiple related constructs. This is for a single item. The constructs themselves do not confound any of the following: stem or valence or construct, right? So what do I mean by that? The item stems. If you always ask a question with the stem, I believe that, I believe that, I believe that, and you have people try to organize. And then one of the questions was, I think that. And then the other one was, I believe that, I believe that. Turns out that I think that the different stem may cause people to read it and respond to it a little bit differently, which shows up in your analysis. Valence is another term for positively or negatively worded, right? So if you say, I believe that, or you say, I don't believe that, those are backwards. In negatively worded items, we often, in historic terms from psychometrics, we'll just take the data and convert it, take the highest number and subtract, plus one minus the score. That's not enough. That changes the right direction, but that's not enough. And then finally, the construct itself. I've seen people create scales where you might take for a given construct all the same stem, but then in another construct, it wouldn't be the same stem. So like for instance, if I'm measuring happiness, I believe I'm happier today than I was yesterday. I believe this, I believe that, right? There's happiness. And I'm going to go measure willingness to, my empathy for others. Let's call that one, right? And in my empathy factor, I say, I think. My stems are different. My factors are different. Now I have a confound. Are my item responses different because of stem? Or my item response is different because of factor, right? So now when you build items, you have to think about the design. The items themselves are like miniatures experiments, right? And when you think about when people respond to them, you have to think about balancing stem, valence, construct across. Otherwise, there's no statistical control that you really can do, right? And yes, you can avoid the need to reverse code by rewriting items as well. I hate the reverse coded items. I think they were always used when I was growing up as a kid. I was told those were used because it was our way of making sure someone was paying attention and not just, well, we have other ways of doing that now. Attention checks. The answer to this item is B, something like that, right? There's, MTurk on Amazon, I know, has a lot of different ways of doing that. Yeah.
So what do you say to the person that says, you have to use this questionnaire that was written 60 years ago when we began,
Yeah.
and those items are terrible according to our current standards of how we need to measure?
Well, it's tough if they've already collected data with it because the ship has sailed. But if you're getting into that situation, they haven't collected data yet. One of the preliminary studies would be to update it, change the bad items, and do a measurement study for it. Basically, see how related that new version is to the old version. But if it has better properties, if it still measures the same construct but has better properties, that'd be what I would say to do. Yeah, but you can't just do that. So, like for instance, in certain fields, there's these gold standard scales, right? Right. Like depression inventories or otherwise, right? I remember Lisa worked with a group of people who used something called the Behavioral Assessment Scale for Children, the BASC. And when they collected the item level data, it never fit. It was a multi-factor model. It never fit. And then we looked at the technical manual for it. The higher order model it had an RMSEA, I kid you not, 0.21. That's how bad the fit was, right? It was bad. Well, yeah, exactly. And what are people saying? Well, we can't not use it because it's so established in their field. If you submit a journal article where it's not being used, now you threaten the validity to the reviewers because this is now the way that it's measured. So the other way I would look at it is, okay, so then you have to work, if you're really concerned about it, you have to build evidence to suggest it's bad. And the way you usually do that is an updated to it, but that takes you away from your study. So there's no easy solution in some cases, some fields. Alternatively, do two analyses and compare and contrast them. All right. Why might these items have problems? How important is you? Well, how important is you on a scale of 1 to 5 that my family members have good relationship with extended family members? Well, what if you don't have any of those, right? My family is physically healthy. What if you don't have a family? Yeah. What is the quality of the relationship you have with your children? What if you don't have children? These are actual items that she had to answer, like when she didn't have kids. I think she made a list of these. To what extent did others make it difficult for you to engage in various activities before your imprisonment? Said it include prisoners. I rarely feel sad. It's a hard one. What is rarely? I feel sad. I can see with that. I feel sad often. I feel sad rarely. I don't know. And then there's no neutral option. I don't know. This is an actual example from valence and constructs. So each of these bold-faced names are different factors. Those are the items that seem to measure them. And you'll note here the lack of emotional awareness all had reverse-coded items. That's not good, right? Similarly, the first items on the scale did not have the referent when I'm upset. So all these other ones, when I'm upset, shows up everywhere in the title. But until you get to either lack of emotional awareness or all of lack of emotional clarity, right? So, yes. So you can reword this, but really there's basically, if your data are already collected, so you can't fix anything, there are three basic choices for method effects. In the model itself, you can expect there to be some type of additional correlation between observable variables. Now, again, we're in a spot now where we're moving into method factors. This is not a higher order term. People sometimes conflate the two, but let's not right now. The error, so you think about this, these are observed variables. If there's a design effect, then if there's something that you did, let's say, for instance, all the items that have when I'm upset in the stem, I'm going to guess are going to have a different covariance than the ones that don't. right? And so each of these might need a residual correlation or the lack thereof, something along those lines. So you can add error covariance or residual covariances. You can create separate latent factors. So for instance, well, I'll get to that in just a second. In that example before, there might be two factors, right? One for positively worded and one for negatively worded. Right? Or you could do something called a bifactor model, which is sometimes called a method factor model. It's a general factor, so that's the trait you're interested in, with one or more specific factors that sort of soak up variability based on valence or design or something along those lines. So, give the example of error covariances. Error covariances are only going to be possible when there's a saturated model in terms of not a higher order factor model. Sorry, no, only possible when there's a saturated measurement model. That means confirmatory factor analyses or estimation of discrete data using the limited information field that we're in. Technically speaking, you can do this in full information as well. Actually, no, you cannot easily do this in full information. You could do a full information IRT model of this if you treated pairs of items as a categorical distribution where there'd be like a log linear model linked to it, but people haven't really talked about that a whole lot. So you need a method factor. Method factor, again, is so predict two items with a method factor, fix both. If you're predicting only two items, the loadings will have to be one. Remember, a two-item factor, you have to make some constraints. But basically what we're talking about is there's two-factor models. This model, right, the two-factor model right here, if you had 6 observable indicators, right, 4 of which we're talking about social interaction anxiety, and 2 of which we're talking about public speaking anxiety, you could make a measurement model that separated both of those. Alternatively, equivalently, actually, an equivalent model would be to say you have one general social anxiety variable, but then for the items that we're talking about public speaking only, you could say that they would likely have some error covariance in addition to it. Now, remember, when I talked about general social anxiety or adding error covariances to factor models, I'd say it violates the idea that these items are independent conditional in a factor, meaning we can't just call this general social anxiety. We have to call it general social anxiety and stuff. But in this case, you know the stuff, right? And so you can actually make that part of your definition. And then the third version of this is to take a social anxiety, social interaction anxiety factor, have it and measure all 6, and then for only the items where public speaking is, have a public speaking factor. Now, both of these, because there's only 2 items, we'll have to set the loadings to 1 to estimate it. We can do that. This latter part, this is the factor you're after, social interaction anxiety. It is uncorrelated with public speaking anxiety by definition in this case. And what it will do is basically public speaking anxiety controls for the presence of public speaking on these items, thereby making the remainder of it social interaction anxiety. Basically the idea of an omitted variable, a bias and regression, which I was speaking about in an earlier part today. So these are what we're talking about. The method factor and the higher order factor show up quite a bit. That is good stuff. This is an example from life orientation. What we have here are 4 models. Here are the items themselves. The 4 models are a single factor model. 2 factors due to wording. Right? So the wording, you've got positive and negative wording right here. You've got a 3-factor bifactor model, right, where you would have a positive wording, a negative wording, and an overall factor. And there's another version of a random intercept 2-factor model as well. There were 4 ways. Those are the 4 ways they tried to introduce how to deal with method effects. again, this is the M plus code for it. If you're doing this in Lavon, it's the same. When you define your latent variable M plus, where you see by, impute in your word in the Lavon land, equal tilde. That's an equal tilde, right? So by is equal tilde. It's the same idea. Unlike Lavon, we don't need plus signs between the right-hand side under by statement. Yeah, we're getting close to the end of the time here, so. The bifactor model is a very interesting case of a model. This had a resurgence. There was a version of bifactor model. Now, everybody who's not asleep yet are about to go to sleep. So this is a sleep warning, right? Give you a little nap before you go home. Okay. In the 1930s, there we go. There was a bifactor model created to sort of in factor analysis. And then in the 1950s, there were people who, Schmidt and Lehman, there's a famous paper by Schmidt and Lehman that described how the bifactor model and the higher order factor model were interrelated under certain conditions. So and sort of both of these models have been around, but bifactor models had a resurgence of popularity in the 90s. There was Hedeker and Gibbons did a paper showing how to do this with item response theory, so it brought a whole bunch of other people in, had this resurgence, and they're back. You'll see these a lot. But basically, bifactor models has a general version of the trait, and then specific optimism, specific pessimism themselves. But bifactor models are weird because you might be much more, it depends on which trait you're interested in, right? Are you interested in general optimism, right? But because each of these items measures general optimism, but some items are controlling for specific optimism and some are controlling for pessimism, right? So what you're getting from a bifactor model in this case is sort of what's left over after controlling for these factors, right? So where I've seen this go awry sometimes is in educational measurement, right? If these were test items and you were saying, oh, I'm going after your math ability, but I got to control these first ones were word problems and these second ones were not, then math ability is true, but now you've controlled for math ability that's not word problems and math ability that's not numeric problems. What I'm getting at is it's no longer just math ability. It's now math ability with other things pulled out of it because they're controlled for in the model. So bifactor models induce additional layers of complexity when it comes to describing what they do. Yes?
In your situation you just described,
Mhm.
it'd be better to make it a hierarchical model in which you could have like variable pathability and then have that go branch off to the other two.
Yes, yeah, something that wouldn't specifically control for it. And why I keep thinking this, when you look at a path diagram and you see an item that has two arrows meeting at it, it's not a collider. No, I'm just kidding. Is it a collider? I'm thinking causal inference. I hear these words and like, anyway, yes. That was an eye roll for those of you on YouTube. Yes. Okay. But what happens when I1 has two arrows is I1, write out the regression equation. I1 is equal to, intercept plus slope times general plus slope times specific. Well, in that case, go back to your regression interpretation. That slope is now controlling for general is controlling for the presence of specific, right? Which means now whatever's left over for you to give you the information for general is now controlled for specific. So bifactor models will fit data amazingly well. I'm like people when they start analyzing data, they do this. It's almost like saying the general factor is everything else that the specifics aren't picking up. Another way to put it is error due to a person somehow. Right? So bifactor models they're somewhere between fool's gold and amazing. Yeah, this describes everything. What's that? Yeah? Yeah. Another version of a bifactor model is a random intercept model. This random intercept model is interesting because the random intercept factor constrains its loadings to 1 to make a random intercept itself. I don't do a whole lot with it, so I'm going to just kind of skip it. This is an example that Lisa created in a paper she did working with people at University of Kansas. And they had to come up with, for each one of these factors, there was a self-positive, self-negative. These are valent items. This is something about self, other, and situational forgiveness. You have forgiveness for yourself or others, or whether you forgive the situation. But the items were balanced in how they were worded, but she had to come up with each of these. So you would imagine what would end up coming from this is a situational overall factor potentially for each of these. Yeah. Yep, there it is. Or there's another way of looking at this is here, where you've got the positive items, the negative items, controlling for each of those, and then you've got the self, other, and situational bifactor approach to it. All right. Just throwing things up here. So there's an example online in Laban if you want to see how to do this. So I'm just going to point you to that. I'm going to wrap up today, and then next week we're going to talk about one last consideration we have to do before we get to that full structural model that I started the class with. Kind of an odd way of putting it, right? But basically, next week's class is measurement and variance. The idea meaning that we may have to control for the influence or the difference. There may be different types of measurement for different types of groups of individuals, right? So to look about that. But today, fitting was sort of leading into this concept that really need next week. Fitting measurement structural models are sort of two different issues. Right? When I say this, the measurement model is the lower order factors. When I said we got to start there and estimate that model, and then we worry about the higher order factors or something else, right? So measurement model includes, am I going to treat these as method factors? Am I going to treat these as a higher order? Do I have a bifactor model? How am I doing that? A structural model then becomes, do I have higher order factors in what I'm doing, right? And in almost everything that we do in SEM, this is going to play out. This is a concept that really holds. It doesn't solve all the problems by any means, but it's a lot easier to take your measurement models and estimate those first, because those are the ones that you have to refine to get model fit. Those are the ones where the model fit is likely to be the worst. It's the ones that have the highest degrees of freedom usually in a path analysis. So you get into your measurement models, you make sure each one of those fits. If you have three different separate factors, look at them independently, then put them together and look at them, right? That's it. Measurement models first, and structural models. It will help you limit the source of misfit. This is what's going to happen next week as well, too. We're going to get into whether or not what we were seeking to look at was the very first question we asked class was, what's the difference, what's the impact of marital status on happiness? Well, we've got two groups of people, married or not, and we've got happiness, right? Well, happiness is a latent variable. We had to define its measurement model, and then we have to go and test whether or not those groups, if there's group differences on the items, before we can think about group differences on the structural trait, right? So there's ways that we have to build in, but all of that together is being built from a measurement model first, then a structural model, and then that last concept will hold with us when we get to the very last class and I actually do it all together. All right? See where we're going. Any questions about class, structure? Now that you submitted your homework, your test feedback, I will take a look at that over the next week and add to your test grades. I wasn't planning on going over the test since I had you go over it again, but next week I'll open up and ask if anybody has any items they'd like to go over a little bit as well too, to sort of reinforce that too. Okay? All right. Thank you for your presence. It's the highlight of my week seeing you all, and see you next time.